We are now in lesson 10 through 12, which is about proportional relationships and constant rate. And this is us moving towards taking those equations that we're learning about and graphing them. So let's start with some base vocab that we need to know in order to understand the rest of this lesson. The very first word that we need to know about is what a proportional relationship is, just for us to even learn a lesson about it. So let's get down the definition of proportional relationship. So a proportional relationship is a relationship between two variables, and it's just saying that they're going to change into relation with one another, meaning that if we change one of them, the other one's also going to change. If we increase one of them, the other one might also increase or decrease because the other one went up or down. So that's a proportional relationship, and you'll see that in equations. If x equals y, if we put something in for x or change what x is, y is also going to change accordingly. So now let's get down the definition of slope. There's a lot of different ways of thinking about slope. The first one is that it's how steep a line is when you graph it. So if it's super steep, then it has a high slope. If it's not so steep, then it's a low slope. The next way of thinking about slope is the rise over run. So if you take a look at how much something goes up, and then divide that by how much something goes over, that is how you calculate slope. So it's rise over run, which is how much you go up divided by how much you go to the right. Also, the last thing you want to put down is that your rate equals slope. And we'll get down the definition for rate in a second, but you'll want to understand that slope and rate are pretty interchangeable. So now let's get down the last definition we need, which is rate. So just like with slope, there's a lot of different ways to think of rate and what rate is. So rate is just how fast you're going. So I ran 3 miles in, 30 minutes. That's my rate. That's how fast I was going. So you can also think of it as your speed. The way you calculate your rate is you do your distance divided by your time. So in those classic math problems, John traveled 5 miles in 10 minutes, you're going to divide those to get the rate or the speed. You can also remember that rate equals your slope. It's just the way you think of it is rate is your slope when it's graphed. Okay? So if you take your rate and you graph it, that's going to be your slope. Because we're now really working into talking about constant rates, which is talking about just how fast things are done or how fast you're going to be traveling, you need this really important equation that I like to call the dirt equation, because it just reminds you of what's in the equation. So let's get down the dirt equation. So the dirt equation is your distance equals your rate times time. So a lot of times you'll just write it down as D equals RT. Dirt. That's why we call it the dirt equation. And you're going to use this for all those sort of problems where it's so-and-so traveled so much in 5 minutes, or they were able to make 5 bracelets in 2 hours, because you're going to be able to use that or finding rate, or how much time, or how much they completed. So distance may not always be distance, it might be how much they completed in that time, making jewelry, mowing lawns, and such on. So what we're going to do is we're going to manipulate this equation to show what each of these will equal, so that you know how to solve for that if that's what you need. So we already have D. The distance, if you need to find the distance, you just need to do your rate times your time. So if you need distance, or you need the amount that's going to be completed, you just need to take the rate that you're working at and multiply it by the time. Now, what if we need to find the rate? Well, if we need to find the rate and we're given distance and time, all we need to do is manipulate this equation to solve for r, meaning get r by itself. And we just learned in our last lessons that, well, if we want to get r by itself, we need to undo multiplying by t. So we would divide both sides by t, and you'd end up that r equals d over t. So you need to take your distance, or how much you're completing that amount of time, and divide it by your time. So anytime you need to find your rate, or your slope, or your speed, you're going to take your distance and divide it by your time. Lastly, what if we want to know the time it takes to do all this stuff? Well, just go back up here. If we want t by itself, we're going to divide both sides by r. So t equals the distance over the rate. So this way you're going to have a fast way of finding anything that you need based on this equation. If you need the distance, multiply the rate times the time. If you need your rate, you need your speed, divide the distance by the time. If you need the time, divide the distance or the amount of stuff that you completed by the rate. And you're going to use this a lot, especially as we get more into graphing. There's one more equation I want us to take a look at. This last equation, the reason I wanted you to look at it is it's basically the dirt equation, just in a different form, in the form that you're going to see more commonly in algebra. So normally our distance, or the amount of stuff that we need to complete, is going to be your y. Your m is always going to be your slope or your rate, and x is going to be your time. So y equals mx really is the dirt problem, just in a different form. Just your distance you're putting as y, and you're going to need to start getting used to as being your rate or your slope, and we normally put x as our time. So this really is the dirt equation, just in a different form. So whenever you come across having to write an equation for these sort of problems of so-and-so did this much stuff in this amount of time, instead of writing it as d equals rt, you're actually going to put it in y equals mx form. So now actually let's try an example of that. So here we have an example of a problem that you're going to see a lot more as we move into algebra. Jamie runs 3 miles in 27 minutes, so a lot of us can do the fast math of, okay, that's 9 minutes per mile. Kind of slow, but not too bad. Assuming she runs at a constant rate, write an equation that represents how many miles, in y, she can run in x minutes. And we need to write an equation from this, and so we're going to be writing it into the form of y equals mx form. So we don't need anything except to find m. We need to find what that rate is, what her speed is. Well, we know from the first thing we did that in order to find rate, you just need distance and time. So if all we need in order to find rate is distance and time, whoa, that's exactly what we're given. So let's throw those in. So our distance was 3 miles, and our time was 27 minutes. So you could turn this into a really nasty decimal, but let's just stick with fractions, and this is a fraction that we can reduce. So her rate is 1 over 9. She's for every mile, she's doing it in 9 minutes. And we can just take that rate and put it into the equation. Y equals 1 over 9x. And there's your equation. That's all you need. We just needed the rate to put it in. Now let's take a look at how this looks when we graph it. So we're going to be graphing our equation y equals 1/9 x and see what that looks like on a graph. Now, this is a t-table. You might have recognized that from 5th and 6th grade, where we get to choose some numbers to put in for x and then figure out what the y is and put that on our graph. So we get to choose what numbers we want for x. A lot of times I like to start with simple numbers, 0, 1, 2, but you can already see, if I put in some of those numbers, they're going to come out as fractions. So you want to choose numbers that are going to come out as nice numbers to work with. So 0 will work out nicely. If I put in 0 for x, well, 0 times 1/9 is still 0. So our first point is going to be at 0, 0. Next nice number to put in, maybe 3. 3 is not too bad, because if I put in 3, that ends up being a third. And 1/3 is not too bad of a number. What else can we put in there? How about 6? Okay, we can put in 6. That makes it 2/3. And then 9 will come up to being 1. So those numbers aren't too bad, and now we can put it on our graph. Now you'll notice this graph doesn't have its axes labeled. So sometimes in your homework, it will have the axes already labeled for you, and it's going to decide what scale you're using. Sometimes it will be blank, and you need to decide for yourself. So we need to decide what our scale is going to be. So the bottom is x, so this is our time. So we should probably just do per minute. So let's put down the minutes for x. 1 through 10 sounds pretty good for minutes. Now we have to decide, do we want to put the y's as ones, or maybe you want to do every 2, every 3? Well, let's take a look. These numbers are pretty small, so maybe even doing each one is going to be too small. Maybe we should do every one as a third. We're allowed to do that. It's our choice. So maybe this first one's 0, and then this is a third, this is 2/3, This is a whole. This is 1 1/3, 1 2/3, 2, 2 1/3, 2 2/3, 3, 3 1/3, and 3 2/3. Okay? You always get to choose your own scale if they don't provide it for you. So now we can take these numbers and put it in. So we have, the first one is 0, 0, which makes sense. If time hasn't started yet, she hasn't moved. So our very first point is 0, 0. Next, we have 3 1/3. So we're going to go over to 3 and then up to 1/3. Next, we have 6 2/3. So we're going to go over to 6 and then up to 2/3. And lastly, have 9 and 1. So we're going to come over to 9 and then go up to 1. And you should see a pattern because this equation is linear, which means when we graph it, we should have a straight line. So you should see a pattern that, oh, every time I go up 1, I'm going over 3. And that's exactly what slope is. So now we can just connect these lines. And the reason I'm putting an arrow on that end is this line goes on for forever. So that way we can predict however much time has passed, how far she would have traveled. Okay? And also don't forget the last thing that we probably should have done at the beginning is to label the units we're using. So down here, we're using minutes. And over here, we're using miles. That way, it's really easy to look back and see if your graph makes sense. So in our graph, it's saying after 9 minutes, she's completed 1 mile. Yeah, that sounds about right. So then, like at 4 1/2, she's completed half a mile. Yeah, that sounds about right. And we could extend it out if we needed to. And that is it for this lesson.